What is it?
Okay, so for 9, right? Alright. So you have this inequality that the natural log of n is less or equal to n to the a, right? And this is, it's for a sufficient large n. What does that mean?
It means once n gets big enough, this works.
How do we know our n is big enough?
That doesn't matter. So the inequality that the book gave us actually uses that word. If you go back to, I don't know, I think it's question 33 from whatever it was, they use the wording for sufficiently large. And for us, it doesn't matter what the n is. We don't need to find it, because the whole point is that eventually, for some value of this lower limit, it's going to work. And that's all we need. Because let's say that it was n equals 10. So if we could say for n equals 10 and do all this stuff, if the series converged, starting at n equals 10, all this does is add a few more terms, it's still going to converge. Or if it diverged, adding a few more terms isn't going to help the divergence. So that's why it doesn't matter what the n is. Sometimes you'll see the wording, instead of saying for sufficiently large n, it'll say something like, there exists and they often use capital N. Capital N greater than or equal to little n, such that blah, 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 blah. Like this part here. And that's another way of saying eventually it's going to work. And that's good enough. Any other questions? Yes, Kim? 27 and 29, yes.
So why is it that for 27 you have to do a second, like a second test with the limit test, but on 29 you don't? So 29 you just say that it's constant, decreasing continuously.
Well, let's see here. So for this one, I chose to use the integral test. Let me see what the difference is with 29. So 29 is using the alternating series test. And this isn't the only way to do it, but what I chose to do when I was doing these solutions, 29, I use the alternating series test. All you need to do is show that the nth term is decreasing and it tends to 0, and boom, it's going to converge by the alternating series test. So that's all I had to do. Since I chose to do the integral test, but did I have to? Well, anyway, I chose to do the integral test, so that's just then going to do this. If I chose to do the alternating series test, the problem was, how do we know that this is decreasing and tends to 0? Well, for the alternating series test, you need those two conditions, that it's decreasing and tends to 0. So, now this one actually, you could have, because, and it wouldn't have taken that long to actually prove it. We can't, because of that negative exponent, the absolute value of a sub n is n squared over e to the n cubed over 3. This guy's exponential, that's quadratic. Exponential is going to overpower quadratic, so we could see that this is going to tend to 0 pretty easily. Decreasing, though. Do we know that this is always decreasing? Seems like it should be, but do we know it? So we could do like the, could find the derivative, and I'll bet you we could probably show the derivative, like if we factor the term, factor the derivative, we could probably show that way that it's always decreasing. But I don't know when I made these solutions why I went with the integral test, but that was probably why I didn't do alternating. and it's easy to integrate. So, any other questions? Oh, yes, Sid.
34.
The Leibniz test cannot be applied to blank. Why not? Show it converges. Is this the one?
How do we know that the second part where you say the original series is equivalent to, and then that, and then you kind of prove that it converges from.
Ask that question again. So,
Yeah, I mean, I was wondering if you could explain that last part where you prove that the original series is convergent.
oh, so if we rearrange the terms, then putting all the positive terms together and all the negative terms together, we can see that it's just two geometric series.
Wait, so I thought, wasn't it like you can only rearrange terms if it absolutely converges?
Yes, but just because of and so I should have shown that it does absolutely converge. But so that's my bad on this, but just know that just because the Leibniz test can't be applied does not mean it won't absolutely converge. So,
It does absolutely converge.
well, if it can't be applied, because this says it can't.
Oh,
Why can't it be applied?
well, yeah, that's not decreasing.
Right. We do have an alternating series, but it's just not decreasing. So yeah, I should have shown that this absolutely converges at least. But anyway. Any other questions? Can I have your homework then? And I do have a reality check for you. Yay!
That's better than. Oh, really hard.
I want to say it was. I remember thinking,
I am on my fourth one and I got
it was. I was actually. Alrighty. There we go, 6 minutes on this one. I think they go quicker if it's on. The longer one is no! That's disgusting. Paper poop is evil. You should have done red. Oh, ooh, ouch. I was gonna say red paper. How are you gonna read it? I could have done pink though. Yeah, I didn't think about pink. Did they get maybe they? Oh no, they didn't. They got so at least I did the same thing. Sorry. Everybody got one? 6 minutes, go. on the recording. Okay, so any questions? Let's look at number 2. Oops, gotta go over here. There's number 2. I didn't really know what to write for an explanation on this one. Does anybody need an explanation for anything? Are you ready for number 3?
Yeah.
So remember when you compare the nth partial sum to the next term. So the a sub whatever should be the next term after the partial sum. Any questions at all about the reality check? Today's lesson, the good news is, I think it's kind of a little breather. I mean, we are going to learn 2 new tests, but they're not that hard. These are the last 2, though. I saw the look on your faces. This is it. Oh, right. Yeah, there's more, but this will be the last tests. Okay, let's go ahead and... Yeah, don't give away anything. Whew. Ratio and the root test. That's right. The ratio test is going to become very important for us in subsequent sections. All right. Let's do it. Let's write these tests down. Actually, let me get it. Okay, here's the ratio test. Let's start with that one. With the ratio test, we are going to assume actually, before we assume, let's define something here. We are going to consider the series, the summation of a sub n as n goes from 1 to infinity. So a sub n represents the nth term. And then we're going to assume. And yes, I do know what happens when you assume. Assume the limit as n approaches infinity. So this is called the ratio test. It must involve a ratio somehow, and it does. It is the ratio of 2 consecutive terms. That is the ratio. But it's always, when you look at the 2 consecutive terms, it's always the second term over the first term. Always a sub n plus 1 on the top. So we're going to assume that this limit equals L, that this limit exists. If it doesn't exist, you can't use the ratio test. So here's what it says. I have no idea what you guys are laughing about. If L is less than 1, the series converges absolutely. If L is greater than 1, the series diverges. And what if the limit is equal to 1? The test fails. I know, right? Big fat F for the test. It's inconclusive. You have to try something else. And there you go. That's all there is to the ratio test. It's pretty easy to see why this one works because, oh, yes, Karen.
Why does the test fail with other
Well, let's talk about why it works. Which will sort of answer it, but not really. But anyway, maybe. I'm going to do like not a formal proof, but a very loosey-goosey proof. This ratio, does this, I mean, I don't think we actually, maybe we did. I don't know. Anyway, does this ratio look at all familiar to you? Have we talked about the ratio of two consecutive terms at all, perhaps? Like maybe a certain type of sequence that had a, yeah, it's our R. It's the common ratio in geometric series. So we're not saying that the ratio has to be a constant R like it is in geometric series, but if the limit of this, if we consider it acting like our R, so we know that if R is less than 1, now we're already doing the absolute value, so that's why we don't need to say the absolute value of L, but we know that if L is less than 1, then the series converges. If L is greater than 1, the series diverges. Now, the L equals 1 on a geometric series. If R equals 1 on geometric, what was that? Was that converging or diverging? Yeah, that was diverging. Here, remember, we don't have a constant R. So, it may be close enough to converge. It may not be. And there you go. That's kind of the thought process with this. There's a more formal proof. I'll actually show you a semi-formal proof for the root test, and the ratio test is very similar. So that's why I didn't want to bother going through the ratio test, because it's similar to the root test, and I can explain the ratio test with R. So anyway, that's why this works the way it does, and it's also a way to remember it. So there's a ratio test. Let's do the root test, and then we'll look at some examples. So, everybody got this down? Anybody need it still? Aight. The root test. Let's make that a capital R. The root test. Again, we're going to consider the same series. Summation of a sub n as n goes from 1 to infinity. And we are going to assume that a particular limit exists. Now, if the other limit, or if the other thing was called the ratio test, and the limit involved a ratio, and this is called the root test, I'll bet you don't know what the limit involves this time. It's a derivative, yeah, and a banana. Yes, love it. All right, it's, the limit as n approaches infinity. Actually, apparently it's a root. Who knew? Who could have seen that coming? But specifically, it's the nth root of the absolute value of a sub n. And again, let's assume that this limit exists. Well, guess what? I get to just do a copy. I know, right? And paste. God, why aren't you guys done writing this down yet?
I am.
Oh! So we got an email from the principal over the weekend that apparently where we get the paper from for making photocopies, I don't know how severely they're limiting our supply, but they're limiting our paper supply because there's a paper shortage. There's a shortage of everything. And I'm just thinking, I'm sorry, math, paper, we need it. Math needs paper. Or iPads. Or Android tablets. There's a new Android tablet, Samsung S8. Looks like a good one. Yes, Adon.
So, if we're given, like, a series way, we can just test both, or we would be figuring out which test to use?
I actually have one of the handouts I might as well do it now. We've got both tests written down. This is from a different textbook, but it's got strategies for choosing 5. Sorry, I got the email about, watch the paper after and don't think that it doesn't mean we're not gonna have reality checks. Anyway, we're gonna have reality checks, don't you worry. That's right. So if you guys look at this, let's see, which number is it? So number 7 talks about honestly, number 7, I mean, if a sub n is of the form b sub n to the nth power, if you have an nth power in there, the root test might be useful. Like, that's the whole point of the root test. Not really the whole point, but it's the most common thing is we want to get rid of that exponent of n. So, oh, and then number 6 talks about using the ratio test. One thing I don't think it says it here. I can't remember. But anyway, if you do, this goes true for ratio or root. If you do one of them and you get a limit equal to 1 and the test is inconclusive, don't bother trying the other test. It's still going to be inconclusive. So try something else. Alrighty. Yeah. Anyway, let's just quickly, I'm not going to spend a whole lot of time on this, but it'll be in the notes if you want to look at it more. Now I've left some things out, but this is a pretty good enough proof without getting bogged down in too many details. The root test is a little harder to see why it works. So let's look at the root test. First of all, assuming that the limit exists and it's less than 1. Let's see what happens here. So there's going to be some r between L and 1. There has to be. We can always find something in between two numbers. So assuming that's true, then let's take a look. So we know the limit is equal to this, L is equal to this limit. That's just how it's defined. And I can just rewrite it like this. Now, because L is less than r, and remember that's because we're defining it that way, then, and here's the thing we were talking about when we were going over the homework, there exists an n such that blah, blah, blah. This is just saying that eventually this is going to be true, that we will have the nth term always less than r. So if the limit approaches L, eventually we can say this. And then just raising each side to the nth power, we get this. And then looking at this series, well, that's just geometric. And remember, again, we've defined r to be less than 1, so we know it's a convergent geometric series. And then that means that this series is going to converge by the comparison test, which means our original converges absolutely. So that's what happens if L is less than 1. Now, if L is greater than 1, then what happens is eventually the limit, so that means the limit is going to be greater than 1. So that means eventually the absolute value of the nth term is going to be greater than 1. Eventually, like all the terms will become greater than 1. And if that's true, then it's going to diverge by the divergence test. So you can do something similar with the ratio test to get like a more formal proof. But I think a ratio test is easier to think about comparing it to geometric series. So any questions on this? You won't have to be able to reproduce this at all. This is just kind of a rough reason why. All right, because what you are going to have to do is, let's get past this real quick, is do problems like these. So you try these 3 problems, and how about, I'll check in at 11:40. Yeah, I mean 10:40. How about 11:40? I'll give you an hour and 10 minutes. I'll check in at 10:40. We'll go to 10:45 if we need to. All right, I'll give you a little bit. Let's see here. If I define a sub n to be that, then the limit is this. So just multiplying by the reciprocal. And it will simplify to this. What? Way. Yes. So we can see the limit is going to be 1/3, which is less than 1. So we know it converges. So that's number 1. I'm going to go ahead and shrink it a little bit. See if I don't have to shrink it too much. I'll leave that up and put 2 and 3 back up. Is that too small? Well, but let's get that off of there. There you go. L'Hopital's rule and all that. So root test seems to be a little difficult. So if we do the ratio test, we can simplify it down here. Now remember this guy right here, if you haven't worked with factorials before, this fraction here, n factorial over n plus 1 factorial, hidden inside the n plus 1 factorial is an n factorial. Like let's just say if n equaled 3, then n factorial over n plus 1 factorial would be 3 times 2 times 1 over 4 times 3 times 2 plus times 1. So you get 1/4, which is 1 over n plus 1. So that's how I got this here. So any questions on this? All right. And then another sneaky thing you can do here, because this exponent is n plus 1, and I see an n plus 1 here as a base, I can take this numerator, split it up into these two factors, and then the n plus 1's cancel, and I can rewrite like this. But then I get 1 to the infinity, which is an indeterminate form, and that's the indeterminate form where you do the natural log of both sides, and blah, 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 which I'll show you that work. But any questions just getting down to this part right here? All right. Anybody still need this? So then remember the next part is let y equal that limit. You take the natural log of both sides. This side with the natural log and the limit, you can swap them. I did 2 steps at once. I swapped the natural log and limit and then also moved this exponent out in front using the power rule. But then we get infinity times 0, which is also an indeterminate form. Not ready for L'Hopital's rule yet, but I can rewrite it in this form, which is 0 over 0. Remember, if you get 0 over 0 or infinity over infinity, it is also indeterminate, and that is when you can use L'Hopital's rule. So you take the derivative of the top and the bottom. I didn't want to take the derivative of this one yet. I chose to use properties of logs, and then I took the derivative. So any questions here? This is fun. It just keeps going. I see people writing this down, so I'll pause. How many people watched the Super Bowl yesterday? How many people watched the halftime show yesterday? Wait, hands went down. I thought hands would go up. I actually thought it was a pretty good halftime show. You like what? Oh, yeah? I'm old school, so Dr. Dre, Snoop Dogg, and Eminem. That was good. Those young whippersnappers, though, that they had, I don't know who they are. Who are they? So there's Mary J. Blige, and then who are the other two rappers? Kendrick Lamar and 50 Cent? Which one was which? There was one that was in the house dancing with the girls around him. Which one? That's 50 Cent? He was my least favorite, so I guess I'm not a 50 Cent. That style. I just didn't like the style. All right, you ready? So we're almost there. So took the derivative of both sides, and then it's simplified down to here. Now we know that limit is 1, but that's not the one we want. The one we want, we know, is e. And e is definitely greater than 1. How about commercials? I was grading, believe it or not. Not your test though, sorry. I'm finishing ABs. I'm almost there. I'm like in spitting distance. I'll finish this afternoon. But so yeah, I didn't get to see. Oh my God! But did you see the trailer for Doctor Strange and the Multiverse of Madness? Oh, that's gonna be good. And did you catch? I'm pretty sure that had to have been Professor X. I think they're gonna bring X-Men in. Or are they gonna bring Fantastic Four? Because then there was that tribunal. What do they call it? The Illuminati. Yeah. And apparently Reed Richards in the comics is a member of the Illuminati. And so, if so, they might be bringing the Fantastic Four into. Oh my God! I'm so excited. Oh, it's come out now. I actually liked the one with Chris Evans, yeah. The only thing I didn't like is how they treated the Invisible Girl's character. She was just basically there because she's pretty. And so I didn't appreciate that part. But otherwise, I liked that one. I never did see the other one with Miles, whatever his name is. That's what I hear. So, yeah. I actually did try finally over the summer. Yeah. All right, you ready for number 3? Nah? Yeah? Okay. Does anybody still need this one? Okay. And then Jurassic World Dominion. That looks good. Those are the only 2 commercials, really, that I paid attention to when those things came on. So I had no idea. I got to go back on YouTube and see all the commercials. Were the commercials any good this year? Yeah? Oh, okay. See, I grew up with, well, I didn't really, it was in my 20s when Jurassic Park came out. But I saw that, when that first came out, I saw it 7 times in the movie theater because I thought it was so amazing. So I'm very excited. They're bringing back the old people. All right, here we go. Here's number 3. That's all there is to number 3. So this time the entire argument was to the nth power. This one is just screaming to use the root test. And there it is. Any questions? Because that's the end of the notes. Told you it was going to be a little bit of a breather day. You guys got almost 40 minutes. You have 40 minutes. Do your homework. Holy crap. I'm going to stop the recording now.